Welcome to part 5 and the last part of our urinary system lecture. Now we're going to talk about all the things at the chemical level that happen to actually keep homeostasis in the blood and keep things balanced in the blood. So remember, the whole goal of the kidneys is not to keep the urine balanced. It's to reabsorb things or excrete things in order to keep the blood balanced. So the urine can change a whole lot depending on what we need to get rid of in order to keep the blood the same. All right, so let's talk about what the blood composition is to start with. Blood composition is going to be depending on a lot of things. Our blood is constantly circulating. We're breathing things into it. We're digesting things into it. Our cells are constantly doing metabolism and giving things off into it. So it's going to depend on our diet, what we ingest, what our cells are doing. I'm going to have a lot different composition in my blood if I'm running a marathon and lots of my muscle cells are doing anaerobic respiration maybe than if I sat on the couch for 3 weeks straight. And then our kidney activity is the last thing. So if our kidneys are not working properly or not working efficiently enough, or they are, that's going to change what gets left in our blood or excreted out. All right, so what can our kidneys do to adjust this? They can excrete nitrogenous waste. So anything that's left over from our cells, that's made by our cells as byproducts of them just doing their everyday jobs, can get excreted out. They can balance our water and our electrolyte or our salt balance. And this is not necessarily things we want to get rid of. Sometimes we need to get rid of some of this, sometimes we need to keep it. So whereas we always want to get rid of urea and uric acid, the nitrogenous wastes, we want to keep our water balance and our electrolyte balance the same. So if we're dehydrated, that might mean keeping some. If we're overly hydrated, that might mean getting rid of it. And the kidneys can do things to keep our acid and base balance the same and keep our pH levels correct. Okay, before we get into how this happens, I want to make sure you're familiar with the fluid compartments. And we saw this a little bit in earlier units, but we're just going to review it real quickly. So you probably know we're mostly made of water. Once we're adults, women are about 50% water, men are about 60% water by weight. So you can blame about half of your weight on water. Water acts as the main solvent for the body. And remember from chemistry, the solvent is the liquid that things dissolve in. Solutes are the things that go in it. So if you're making Kool-Aid, the powder is the solute, the water is the solvent. And there's 3 main places where this fluid that makes half of us lives. The intracellular fluids, or ICF, are the fluid that are actually in our cells, so they make up a lot of the cytoplasm of the cells. The extra, meaning outside cellular fluid, or the ECF, is the fluid that surrounds the cells. So here you can see, even though it's microscopic when we're actually looking at it, there is a little bit of space between all of our cells, and that's full of fluid. They're sort of bathed in fluids, and most of that is water. So that's the extracellular fluids. But extracellular fluids is made of what I just pointed at, which is called interstitial because it's between. That's the interstitial meaning to the tissues. And the blood plasma also counts as extracellular. It's not technically in a cell. It's traveling through the blood vessels, but it's not inside the actual cells. So there's actually 2 places. And the plasma is really important. This is the link between the intracellular and the extracellular fluid. So even though there's 3 places we find fluid, they're all constantly being circulated, constantly exchanging with each other. So if something changes in our blood plasma, that's very quickly going to affect the water that's inside our cells, the water that's in between our tissues. It gets passed on. And there is a really nice image in your textbook on page 532, figure 15.9, and it shows a circle, and it shows how if we're breathing in oxygen and getting rid of carbon dioxide from our lungs, that changes our blood, and then that circulates to all of our tissues to exchange oxygen and carbon dioxide with them. And then if we're bringing in nutrients, we all know that now from the digestive system, that gets absorbed into our blood and gets circulated to all the cells for nutrients. And then wastes are going to get dumped into the blood. So this is constantly affecting each other. There you go. Look at figure 15.9. And before I forget, I didn't say at the beginning of the lecture, this lecture, part 5, matches page 531 to 537 in your textbook. Okay, so the first thing that we want to look at is how do we keep our water balanced? Okay, in order to be hydrated properly, you need to bring more water in than water that's going out. Seems pretty simple. How do we bring water in? Mainly it's through our diet, so eating foods like fruits that contain water and then drinking fluids. We do get a little bit from cell metabolism. One of the products of cell metabolism is water, but this accounts for very little of the water that gets taken into our body. There's a lot of ways we can lose water. One is through our respiration, okay? Our lungs are constantly bathed to be moist, to keep the air moistened, but that means that through evaporation, we're losing some water every time we exhale. Through perspiration, through sweating, and in our stool. You know that our feces contain some amount of water that's not reabsorbed. Okay, when our water levels drop too low, some things happen. This increases the concentration of solute. So imagine if I put lemonade powder in the bottom of a glass and I only add a quarter of that glass's worth of water, that's going to be really concentrated. It's going to be really strong. It's probably not going to be any fun to drink. Whereas if I put that same amount and I add a whole gallon of water, you're probably not even going to taste it. It's going to be too diluted, not enough concentration. We want that just right concentration. So if we don't have enough water, but we still have all those salts in our body, they're going to be really concentrated. Also, the blood pressure is going to drop. If our blood's mostly made of water and we don't have enough water, now we have much less volume, our blood pressure is going to be low because we have less amount trying to pump through our whole system. It's going to have to spread out. Let's go back to that picture for a second. So over here, I think we talked about this when we did the cardiovascular system. We talked about the red blood cells, but this is why it's such a problem to have our concentrations get off. When concentrations are off, water will move to fix it. Okay, so just like if my lemonade was too concentrated, I would add more water to water it down. That's what our body is going to do. So over here, a hypertonic solution just means that there's too much concentration outside. So you can see all this concentration of salt. Maybe this is in the blood plasma that this red blood cell is floating in. It's much, much more than the concentration of salt that would be in a normal blood cell. So water will leave from that blood cell, to go water down all these salts, which is fine because that's evening out the salt, right? Except look what's happened to the red blood cell. It's losing its cytoplasm, it's losing its water, it's going to shrivel up. That's not good. This makes deformed red blood cells, it causes all sorts of problems, and you can see an actual image here. On the other hand, if you have too much salt in a blood cell, then the water from around it, that interstitial fluid, is going to move in, and it's going to expand. This is bad because now we've messed up that nice shape for surface area like we had over here, and eventually this could explode. Okay, so when our water does get off balance, how do we fix it? There's lots of things that are going to act all together to fix it. So first of all, you know when you don't have enough water, you feel thirsty. This is bad because it means you're already dehydrated. So if you've gotten to the point where you are thirsty, you already are lacking water. So you want to try to avoid ever getting yourself to that point. But if you do, there's a thirst mechanism. This is triggered by our hypothalamus, which remember is in our brain, so it's a neural trigger. Okay, and this happens when it notices that the solute concentration has increased. So if it notices that we've got too much stuff and not enough water watering it down. Or when our blood pressure decreases, but this is less potent, meaning that the first one that's going to trigger an alarm is that solute concentration. Our body doesn't like to wait until our blood pressure has dropped because then we're really in trouble. Also, if there's less water in our blood, and that's where our saliva comes from, then our salivary glands are going to dry up. Okay, and this is convenient because they're in our mouth. So what do? We want to drink water to water down our mouth, and by that, we're bringing in more water to our blood. Okay, so number one thing to fix it, we get thirsty. The second thing that happens is, remember, the way we make filtrate in the little nephrons is the high pressure behind the glomerulus. So as that high pressure is going through, that's what's forcing the filtrate into our kidneys. If our blood pressure drops because there's not enough water, then the filtrate's not going to get made as much. We're not going to pee as much water out. So at least we're not adding to the problem. Number 3, vasoconstriction. Remember what vaso means. Vaso refers to our blood vessels, and constriction means they're going to tighten up. So if I tighten up those blood vessels, I don't have as big a hose for them to travel through. That's going to increase the pressure even if I don't have that much fluid. Okay, but all these things are helpful, but what we really want to do is make sure that we're fixing the actual water content. Okay? And the vasoconstriction is regulated by baroreceptors. Baro means pressure. So these sense when pressure drops, and they tell our sympathetic nervous system, remember that fight or flight, hey, tighten up those blood vessels, we got a problem here. What we're really interested in today is the 2 hormones that help ultimately fix the balance. Those are called anti-diuretic hormone. And if you remember when we did the endocrine system, we learned that diuresis means to pee. So anti-diuretic hormone is going to stop us from peeing. And aldosterone, which we'll talk about more. Okay, ADH, which is what I'm going to call anti-diuretic hormone. Remember when we learned about hormones, we learned that there's 3 different ways they can be stimulated. Our brain tells us, and that would be neural. Another hormone triggers it, which would be hormonal, or something in our blood triggers it, which would be humoral. So anti-diuretic hormone, ADH, has a neural stimulus. The hypothalamus says, hey, something's amiss. Osmoreceptors, and osmo refers to osmosis, which is when we were looking at those pictures of the blood cells, movement of water to change concentrations. So osmoreceptors can sense when the solute concentration has changed. So if the water has dropped, it's going to get too concentrated. And this tells the hypothalamus to tell our little pituitary gland to make some ADH and release it. Okay, so what does the ADH do? It goes and talks to those collecting ducts at the end of the nephrons after all that reabsorption has happened or not happened, and it says, hey guys, you got to absorb more water. We need to keep it. We're already low. The last thing we want to do is pee this out. And remember, we were talking about feedback mechanisms. A negative feedback mechanism is when one thing increases, so another thing stops. They have the opposite effect, and that's what's going on here. If the level of water drops, we make more ADH. When the level of water comes back up, then the level of ADH can drop. So think about a seesaw. Okay, and this can work in the opposite effect. One of the stations when we did the endocrine system looked at a medicine called Lasix, which is a diuretic. So instead of an anti-diuretic, now people will be put on a medicine that makes them pee. So people who have chronic high blood pressure, too much volume in their blood, can be put on something that inhibits ADH and says, don't reabsorb water, the pressure's too high, we got to pee some of this out. So they'll be put on a diuretic, which helps their blood pressure. It also means they're going to have to pee more frequently. All right, that was hormone number 1. Here's the second one, aldosterone. And this has a hormonal stimulus. So this is actually a chain reaction. First, we're going to make a hormone called renin, and that's going to make an in-between step, which is going to make aldosterone. I don't expect you to know any of the in-between steps, but I'm going to tell you why we don't just go straight to aldosterone. So first of all, renin is made by the kidneys, and it's triggered to be released when the blood pressure drops. And then it's going to go on to a couple of in-between steps to eventually tell the adrenal glands, remember those sit right on top of the kidneys, to release aldosterone. The reason there's an in-between step is that in-between step goes more than one place. So renin makes something, and again, you do not need to memorize this name at all, but in case you're curious, it's called angiotensin, and there's angiotensin 1 and 2. And those in-between steps are able to go and talk to the kidneys, talk to the adrenal glands and say, hey, release aldosterone because we need to fix this water. But they can also go and talk to other things that will talk to our blood vessels and cause more vasoconstriction. So it's kind of like sending a call blast out. You can hit multiple things all at once, whereas if we went straight to aldosterone, we'd only get the one effect. But all I expect you to know is that once aldosterone is triggered, what it does is not cause water to be reabsorbed. It causes sodium to be reabsorbed. And remember, this idea, circle it, put stars next to it, water is going to follow salt. We want to keep these concentrations the same. We cannot just adjust water without adjusting salt, or we'll throw our concentrations off. If you absorb more sodium, the water will want to go with it. Okay, it will want to fix that concentration and keep it even. So by absorbing sodium, we're absorbing water, and this can keep our entire balance the same. So this is another reason why we have two hormones. Let's go back for a second. ADH, if we've lost water, notice that it's getting triggered by the concentration being off. So it says we have too much solute, we've got too much salt. We don't want to bring salt and water in, we just want to bring in water and fix the concentration. Aldosterone says, hey, our volume has dropped. Maybe we're losing blood somewhere. Okay, maybe we have a cut and it's been hemorrhaging, and so our blood pressure has dropped. Maybe we just donated blood and our blood pressure has dropped. But we don't want to just reabsorb water, because with that blood we also lost all of the electrolytes. So we're going to absorb sodium, water's going to follow it, and now we're good to go. And again, it's a negative feedback. If our BP drops, we make more renin until it's fixed. Then when our BP goes up, the production of renin goes down because we don't need it anymore. All right, I know this is a lot of information. Last idea, we've talked about water and electrolytes, how we keep those okay. We also have to keep the pH of our blood okay. This is the acid and base level, and this is super important. We can tolerate some differences in our electrolyte and water balance for a little while before we really start to have problems. If our pH changes much, it can be deadly. The pH of our blood needs to be between 7.35 and 7.45. That's only 0.1 difference. If it changes, it's not just problematic, it can be deadly. It can kill us. So this is really important. Okay, now 7 technically is neutral. Okay, 7 is not an acid or a base, it's neutral. But our blood, you can see, likes to be a little bit to the base side. So if you're 7.0 to 7.35, even though in chemistry we would call that alkaline on the base side, in our blood it's called physiological acidosis, meaning, sure, it's not technically an acid, but for our blood it's too acidic, it's too much toward the lower side. Acids are things that give off hydrogen ions. That's what H+ is. And lots of the things that happen in our cells, in our regular everyday cell life, give off byproducts that create H+. So give off byproducts that are acid. For example, if we're exercising and we're doing anaerobic respiration, we're giving off lactic acid. That ends up in our blood, and it changes the pH. This is bad because these H+ can go and attack things. They're very corrosive. We don't want them floating out there by themselves. Okay, so what do? There's 3 things we can do. The first thing is we have blood buffers. These are things that are in our blood that are basically sponges for acids. They see an H+ floating by themselves, they grab onto it, soak it up, occupy it so it can't do damage. Okay, we saw this in our stomach. We had bicarbonate that acted like Tums. So when that gastric acid was there, it can absorb it before it got to our stomach lining. Another thing we can do is change our respiration. We can actually make ourselves more basic or more acidic by holding our breath or breathing faster. And here's why. And this hint might be extra credit, but I don't expect you to have it memorized just for our day-to-day class. But if you're interested, here's acid. Okay, so here's H+ out there on the loose, not good. But here's bicarbonate, and I apologize, that should have a negative charge right here. When you combine them, now you get what's called carbonic acid, H2CO3. Okay, so first of all, we've sponged it up, it's not floating out there by itself. And you can see, you can break this apart to conveniently make water, which can be peed out if necessary, and carbon dioxide. Now, hopefully you remember from chemistry that what drives a reaction is getting rid of the product. So if we get rid of carbon dioxide, then this is going to move this way to make more. Okay, everything's going to go from over here and move this way. Okay? If we had enough carbon dioxide, it might start to move back this way. So every time we exhale, we're getting rid of carbon dioxide, then we can take more acid, sponge it up, breathe it out, sponge it up, breathe it out. Okay, so people who are having some imbalances, maybe they have kidney failure or they're acidic for another reason, diabetics have issues with this, can start to hyperventilate, not because they're having a panic attack, but because they're trying to get rid of their acid. But the one we're really interested in is what our kidneys do. First of all, because that's the unit we're in. But second of all, these buffers are great. They're sponges, but they don't actually permanently get rid of it. They just tie it up. Respiration is great. It does permanently get rid of it, but it only works for carbonic acid, and there's other types of acid in our body. So how do we permanently get rid of the others? We use our kidneys. Okay. This is the slowest way, but we can excrete various types of acid and permanently fix the blood. And I shouldn't say permanently because this is constantly balancing. As soon as we get rid of some, our cells have done more metabolism. Okay. And depending on what's going on in our body, in order to keep our blood pH the same, the pH of our urine might change a lot. So remember, this is not about keeping our urine balanced. This is about keeping our blood balanced. So the pH of our urine might be as low as 4.5. If we needed to get rid of a lot of acid to keep our blood right, to keep our blood correct, then our pH might be very acidic in our urine. Or it could be very basic if we didn't get rid of much. Okay, that concludes the last lecture for the urinary system. Again, you're going to want to look at your textbook from page 531 to 537, and then we'll be doing some activities in class in your diagram packet.